Welcome back for another example of determining prime factorization using a technique called stack division, which is an alternative to creating a prime factorization tree. We're going to start with the given number 6,552 and determine which prime numbers divide evenly into the given number, and we'll keep dividing until we have a quotient of 1. Once we have a quotient of 1, we'll have the prime factorization. Because we'll be stacking the division, we'll start here toward the bottom, and we'll start with 6,552. In the first video, we reviewed the divisibility rules for 2, 3, and 5. If you need that review, you might want to watch the first example on stack division. Because this number is even, we should recognize it's divisible by 2, so we'll start by dividing by 2. Let's go ahead and show this division on the side so that we can show our work. We have 6,552 divided by 2. Well, there's 3 2's and 6. 3 times 2 equals 6, and subtract. Be 0, bring down the 5. There are 2 2's and 5. 2 times 2 is equal to 4. Subtract. Bring down the next digit, which is 5. There are 7 2's and 15. 7 times 2 is equal to 14. Bring down the last digit, which is 2. And there are 6 2's and 12. 6 times 2 is 12. Our remainder is 0, verifying it is divisible by 2. So now we have 3,276. Notice how the result is still even, which means we can divide by 2 again. Again, let's go ahead and show the work on the side. Now we have 3,276 divided by 2. There's 1, 2, and 3. Bring down the 2. There are 6 2's and 12. There are 3 2's and 7. 3 times 2 is 6. There are 8 2's and 16. 8 times 2 is 16. Remainder is 0. So now we have 1,638. And again, this is still even, so we'll divide by 2 again. There are 8 2's and 16. 8 times 2 is 16. Bring down the 3. There's 1 2 and 3. 1 times 2 is 2. Bring down the 8. There are 9 2's and 18. 9 times 2 is 18, with a remainder of 0. Now we have 819, which is not even, which means it's not divisible by 2. So we're done with the prime number of 2, and now we'll go to 3. Remember, the divisibility rule for 3 is if we add the digits and that sum is divisible by 3, so is the original number. And since 8 plus 1 plus 9 is equal to 18, and 18 is divisible by 3, so is 819. Which means now we'll divide by 3. There are 2 3's and 8. 2 times 3 is 6. There are 7 3's and 21. And there are 3 3's and 9. 3 times 3 is 9. We have a remainder of 0. So now we have 273. We should recognize that we can divide by 3 again, since 2 plus 7 plus 3 is equal to 12, and 12 is divisible by 3, therefore so is 273. So we'll divide by 3 again. This one we can probably do without showing work. There are 9 3's and 27, and there's 1 3 and 3. Notice 9 plus 1 is equal to 10, which is not divisible by 3. So 91 is not divisible by 3, so we're done with 3. 91 does not end in a 0 or a 5, so it's not divisible by 3. Let's go and see if it's divisible by 7. 91 divided by 7, there's 1 7 and 9. And there's exactly 3 7's and 21. 3 times 7 is 21, so we have a remainder of 0. So 91 is divisible by 7. It's equal to 13. Looking at our prime numbers, notice how 13 is a prime number. So we can divide 13 by 13, which of course is equal to 1. And again, we're performing stack division. Once we have a quotient of 1, we have found the prime factorization. The prime factorization occurs here on the left. The prime factorization of 6,552 is equal to 2 times 2 times 2 times 3 times 3 times 7 times 13. Or if we're asked to write this using exponents, we would have 6,552 is equal to 2 cubed, or 2 raised to the third power, because we have 3 factors of 2, times 3 squared, or 3 to the second power, since we have 2 factors of 3, times 7 times 13. Again, this technique is an alternative to find the prime factorization of a number rather than using a prime factorization tree. Okay, I hope you found this explanation helpful.